All right, we are going to keep going with page 19 of the geometry review packet. And you'll see up at the top of the page, I've put the relevant part of your formula sheet. So it's really important to notice what part of your formula sheet might be useful for each part of the exam. So let's review that really quickly. First up here, we have an inscribed angle, and that is an angle where the vertex is on the circle. It's formed by two chords, and you'll notice that the inscribed angle is half of that intercepted arc, half the measure of the intercepted arc. The next kind of angle is also formed by two chords, but those two chords intersect inside of the circle. And so the measure of one of those angles, which one are they talking about? GDE. So the measure of this angle, and therefore its vertical angle, is half the sum of this arc and this arc. So when I have two angles that are, four angles I should say, that are created inside of the circle, I want to look at the arcs that they intercept. And in this third case, the measure of angle J, which is this angle with its vertex outside of the circle, the measure of angle J is half the difference of the two arcs that are intercepted. So these are the two arcs. I would subtract and divide by 2. So in problems 51 through 56, we're going to use all of these in addition to the fact that when you have a central angle, and that is an angle with its vertex at the center, when you have a central angle, the measure of that central angle is equal to the degree measure of that intercepted arc. So we're going to be using all of these things. What I like to do, rather than just jump to what all of the questions are asking, I like to look at the picture and see what can I gather before I start trying to fill in the blanks. So right off the bat, I see right here what I think is the easiest, and that is a central angle. Just like I just showed you, when I have a central angle, and I know that that's a central angle because it's named circle O, so O is the center. That central angle of 60 degrees tells me that arc AB out here is 60 degrees also. So I'm going to label that on my circle. And I'm just going to keep looking for anything that I notice. I notice out here that I have an inscribed angle. And the measure of that inscribed angle is 20 degrees. So the arc that it intercepts is twice as big. This arc right here, arc FE, must have a measure of 40 degrees. So that actually leaves me with just one more arc around the circle, and that is arc CB, this one right here. And so I know that they're 360 degrees in a circle, so what I'm going to do is I'm going to add up 60 degrees, 140 degrees, 40 degrees, and 42 degrees, take all of those away from 360 and see what's left. So when I add up all of the arcs that I already have, I get 282 degrees. So arc CB must be 360 degrees minus 282 degrees. And I find that arc CB has a measure of 78 degrees. Okay? And with that, I'm going to move into the circle because I have now all of the arcs, and I want to see what other angles inside can I find the measures of. So there are different ways to approach this. What I see next is that this angle FEA, that's also an inscribed angle because its vertex is on the circle. So I look at the arc that it opens up to. It opens up to this 140 degree arc. And I think, okay, this angle must be half as big as the intercepted arc. So this angle must have a measure of 70 degrees. And from there, I can actually keep going and find something else. And again, you can approach this in lots of different ways. But what I next want to find, I'm inclined to find what is this angle in here, angle EDC. Well, that's like this third case right here, where the angle is created outside of the circle. So I say, what two arcs are intercepted by angle EDC? So I am going to show you, this is one arc that is intercepted here. I'm showing it in green. And the other arc that's intercepted is from here all the way over there. And so the measure of the big arc is 200 degrees. Do you see that 140 and 60? And the smaller arc is 42 degrees. So to calculate the measure of EDC, I'm going to do 200 degrees minus 42 degrees and divide that by 2. And that gives me an angle measure of 79 degrees. Okay? And I'm looking for clues or anything else that I can find. Well, this isn't actually related to the angles in a circle necessarily, but I do know this angle right here. Can you think about how this purple angle and this angle that's 60 degrees are related? Well, they make this straight line, or this segment, AE, and so together they must be 180 degrees. So that leaves me with this angle must be 120 degrees. And maybe that'll come in handy, and maybe it won't come in handy. And I'm looking for just any angles that I might be able to find. The next ones that stand out to me are this angle and this angle. And I know that they have to have the same measure because they're vertical angles, but I want to know, what are those angle measures? Well, that's like this second case that we looked at from your formula sheet. And those are two angles that are generated by chords that intersect inside of the circle. So those are my chords that create them. And we saw that they intercept two different arcs. In this case, they intercept this arc and this arc. And so I'm going to add up the two arcs and divide by 2. So this angle here and this angle here, I'm going to find by saying 60 plus 40 divided by 2. And that gives me two angles that are 50 degrees each. So this angle here is 50, this angle here is 50. Well, when I'm inside triangles, like I am in both of those cases, I can actually round out the triangles. I know their measures because there have to be 180 degrees in the triangle. So in this triangle, I have 70 degrees and 50 degrees. Together, that's 120. So this angle over here must be 60. And if I come over to this long, skinny triangle over here, so far I have 120 and 50 degrees. That's 170. So this angle over here must be 10 degrees. And then the only other angle that's standing out to me, are actually two more angles, are this one right here, which I know needs to be 130 degrees because, again, these two make a straight line. They are a linear pair, and so they have to add up to 180 degrees. And then I see this triangle right here, and I can fill in this angle because so far I have 150 degrees, so this must be 30 degrees. Now, like I said, there are a lot of other ways you might have approached that, but hopefully you got generally to the same place. Once I fill in what I think is everything that I might need, I'm going to go to my questions. I think it's easier to start by looking at the whole picture and then answer the questions. So the measure of arc AB is the measure of this arc here. We have 60 degrees. The measure of arc EF is this one. We have 40 degrees. The measure of arc BC is this one. We found that that one was 78 degrees. And the measure of angle AFB. So notice the difference between the arc notation and the angle notation. Measure of angle AFB FB is this one, and luckily we found that right at the end. That one is going to be 30 degrees. The measure of angle FDB starts over here. I always start at the first letter. I go down toward the D and up toward the B. So remember, that's the one we calculated over here, and we got 79 degrees. And finally, the measure of angle FEA is this one that I've labeled in orange, and that one is 70 degrees. So there was a lot of skill work that we did in that problem, but hopefully you made it through very well. When we go on to this next circle problem, this one asks us some different things, more about lengths of segments and than it does about angles. So there's two theorems that I want to make sure I remember, and that is one of them says that when you have a chord, and a chord is just a segment that connects any 2 points on a circle, when you have a chord and you have a radius, well, we know there are an infinite number of radii in a circle, but when you have the radius that is perpendicular to that chord, it bisects the chord. It makes two equal parts, two congruent parts, I should say, out of that chord. It splits it evenly. The other thing that you should remember for this problem is that when you have a line segment that is tangent to a circle, and tangent means that it just skims the circle, touches it only at one point, and you have the radius that connects to that, it makes a 90-degree angle there. So, again, I'm going to read through this information and label what I know. Circle P is below, so that tells me that this is the center. Line M is tangent to the circle at point R, so that's what I was just saying. That tells me this is a 90-degree angle, and so is this, but I only need to label 1 to show that that is a 90-degree angle. So radius PR is perpendicular to line M. They didn't tell me that, but I knew it because line M was tangent. Next up, PR is 8. Well, that's really valuable to know because if PR is 8, every single radius is 8. So PX must also be 8, and it's a little hard to label, so I'm just going to remember that PW is also 8 in case I need that later. But all radii, if one radius is 8, all of the radii are 8. Then they tell me PS is 10. So here I'm going to use a different color and label that 10 units. And if that whole segment is 10 units and from P to X is 8, that tells me that XS is 2. They also tell me that UW is perpendicular to TZ. So this is what I was talking about over here, this first thing to remember. When I have a chord and we have a radius that is perpendicular to it, that chord is bisected. The radius isn't necessarily bisected, but the chord is. Okay, so now let's see what we can fill in. The measure of angle PRS is this one, and they're checking to see, do we know that when we have a tangent to a circle and it touches a radius, that it makes a 90-degree angle? Next, what is the length of SR? This side right here. Well, that's actually not something that we labeled. It's not something that we knew or could easily deduce. But what I do see is a right triangle here. So I am going to use the Pythagorean theorem to find that missing side. I can use a question mark, I can use X, I can use B, whatever I want. But it is the leg that I know squared plus the side that I don't know squared equals the hypotenuse squared. So that's 64 plus question mark squared equals 100. I'm going to subtract 64 from each side. and I get question mark squared equals 36. And that tells me that the question mark side must be 6. I take the square root of 36, and this side must be 6. So SR I label as 6. TU is congruent to which segment? Well, like we labeled on there, TU is half of the chord. It has to be congruent to the other half of the chord because it was bisected, meaning cut into two congruent parts. So I can call it UZ, I can also call it ZU. Angle WTU, that's this angle, is congruent to which angle? Well, it's going to be congruent to this mirror image. And the reason for that is because these two triangles, without going too much into it, this triangle here and this triangle here have to be congruent by SAS. They share a side, so that's the reflexive property. A is they're both a 90-degree angle, and then I prove that those two are congruent. So, by CPCTC, angle WTU is congruent to angle WZU. And TW then must be congruent to, arc TW is congruent to arc ZW. And finally, SX is 2 units. We labeled that before. That is 2 units there. Next, we're getting into the idea of radians. And we have to remember for this part that in an entire circle, there are 2 pi radians. And that means that whatever one radius is, however long that one radius is, it would take 1, 2, 3, 4, 5, 6 and a little bit radians to go around the entire circle. So I can think about doing this problem a couple different ways. One way I could think about it is, oops, I'm not going to draw that part. I could draw a circle and I could split it in half and say, well, I know that if an entire circle is 2 pi radians, half of that must be pi radians, and I could keep, then that tells me that the whole circle is 2 pi radians, and just halfway around it is pi radians. So I could say 1/2 of a circle. Okay? I can also think about it the way I'm going to do number 64, and that is to say I can take the pi over 3 and say pi over 3 is what fraction of an entire circle. Well, this gets a little bit tricky with the fractions, but you have to remember how we divide a fraction by something else. I'm going to think about this also as a fraction over 1. So this is pi over 3, and when we divide by fractions, we multiply by the reciprocal. So I flip this and multiply, and this becomes pi over 6 pi. The pi's cancel, and I get 1/6. So pi over 3 represents 1/6 of a circle. So that's how I would do it just by looking at the numbers. If I want to think about it a little more conceptually, which I might, it's always a good idea, I can think when I take my 2 pi, and that's all the way around the circle, and I split it in half, that's pi. So now I'm only talking about this top half of the circle. And if I split that into thirds, then I get pi over 3. So this pi over 3 is 1/3 of the top half of the circle. So it is 1/6 of the entire circle. And finally, we are going to go on to the very last page of your review packet. And this page of your review packet uses these formulas that I've put at the top of this page. So again, you may want to go back and look at that formula sheet, see what you'll have on your exam when you're actually taking it. But first, we're thinking about radian measure. So again, think about that definition of radian measure. It is saying if my radius is 8, how many of those radii would it take to cover this arc, to intercept an arc of 24 centimeters? Well, 1 would be 8 centimeters. That would be 1 radian. 2 radians would be another 8 centimeters. And then it would take a 3rd radian to get a full 24 centimeters. So that tells me that this is 3 radians. That is the measure. Okay? And to find the area of a sector, well, I have 2 different formulas for sectors, and in this case, I know the radian measure, so I'm going to use this one, this formula over here. I'm going to scroll down so that I can show my work. The area of sector COD is, well, when I think of sectors, and you might use the formula, or this might make a lot of sense to you, I'm talking about an area that is part of a circle. So I'm going to start with the area of the entire circle, and the area of this entire circle is pi r squared. So that would be, if I work that out, that would be 64 pi would be the area of all of circle O. But obviously I haven't shaded all of circle O. I just want part of circle O. Which part of it do I want? Well, my angle tells me that I want 3 radians worth out of, how many are in the entire circle? 2 pi. So this is the part of the circle that's included, and this is the entire area of the circle. So we're taking a fraction of the entire area of the circle. And when I work that out, watch how I simplify this. This becomes 3 over 2 pi times pi times 64. And my pi's cancel, and my 64 and 2 cancel, leaving me with a 32. And I just multiply what's left, which is 3 times 32, or 96. And I want to look back at my units, centimeters, and its area, so my answer is squared. Okay? And we're going to try that same thing with number 66. I say, how many radii would it take to cover this intercepted arc? Well, that one radius would give me 3 centimeters. Another radius would give me the full 6 centimeters. So it is 2 radians to get from Q to F. That's an angle measurement, just like degrees, but it's a different unit. It's a different way of measuring angles. Okay? And the area of the sector, again, I'm going to start with the area of the entire circle, and then I'm just going to take the part that I'm interested in. So this is pi r squared. That's the area of the entire circle. But now I'm taking 2 radians out of the 2 pi that I know are in the entire circle. And that's about 6. So this is about 2 out of 6. A little bit different than that, but that's the general idea. So now I'm going to simplify. So this becomes 2 over 2 pi times 9. And if I want to think about these as fractions also, I think about them as ones. So the 2 and 2 cancel, the pi and pi cancel, and all that leaves is 9. Look back at your units, and they are 9 centimeters squared. And we are on to the last two problems. This time you'll notice that your angles are measured in degrees, not in radians. So I need to recognize that I've been given formulas. Look at these. I've been given formulas for arc length and area of a sector in degrees, in addition to both of those formulas given to me if I'm measuring in radians. So in this case, I'm using those degree formulas. One thing to correct, this is actually a typo on the review packet. This should be, if you look at this picture, there's no U on it. This is arc SW, not arc SU. Okay? And so I'm going to use those formulas up above, and the length of SW, arc SW, is, well, just like we were doing on the last page, or on the last two problems, I should say, I'm going to start with what fraction of the circle are we talking about? We're talking about 40 degrees out of 360 in the whole circle. And when I'm talking about arc length, it is part of the circumference. So 2 pi times the radius. And now I'm going to simplify this. My zeros cancel, 10/10 cancels, and this is 1/9 times, and when I multiply this out I get 18 pi. Well, that simplifies to just be 2 pi is the length of my arc. So this is 2 pi centimeters, and it's a length, so it's not centimeters squared. It's just 2 pi centimeters. If you wanted to round it, you could say about 6.28 centimeters, although that's just a little bit less precise. Then to find the area, again, like we were on the last two problems, except this time we're working in degrees and not in radians. So I'm going to say that the area of sector STW is, it's going to be 40 degrees out of 360. That's the portion of the circle we're talking about, but this time it's not a portion of the circumference, it's a portion of the entire area, pi r squared, rather than 2 pi r. So this is 1/9 times 81 pi. So 1/9 of the circle is what we're talking about, and the whole circle has an area of 81 pi. So this comes out to be 9 pi centimeters squared. And this is area, so I want to write centimeters squared. So that is 9 pi centimeters squared. Again, I probably wouldn't round, I wouldn't recommend it, but you could. It's about 28.27 centimeters squared. Remember what units you're using, area or square units. Linear measures, like arc length, are just centimeters. And finally, we are looking for the length of arc RZ. And so I am going to take the fraction of the entire circle I'm talking about. This is an arc, not a segment. And this is 120 out of 360ths. Can you reduce that in your head? What fraction of the circle we're talking about? And then since we're talking about arc length, it's part of the circumference, so 2 pi r. And hopefully you were able to simplify this in your head to be 1/3 and 6 pi. 1/3 of 6 pi is 2 pi. So that tells me the length of the arc is 2 pi, or about 6.28 centimeters. And the area of the sector. Area of sector RXZ is, again, the same fraction of the circle, 120 360ths. That's the degrees out of the entire circle. This time it's out of the area, though, pi r squared. So this is 1/3 of 9 pi, which comes out to be 3 pi. And again, don't forget those units. 3 pi centimeters squared for area. And there you have it. That's the very end of the MCPS Geometry B exam review packet. So good luck on your exam. If you have any questions, I would take them into your teacher before you get to exam time. Good luck.